Welcome back. Today we are going to talk about how to measure experience. Virtual reality is all about experience. The whole course is about how to improve the experience in virtual reality. In the earlier classes we saw that this course we are going to learn how to improve the immersion effects and the interaction effects. If you want to improve the experience, then the first thing we have to do is to measure the experience. Only when we measure experience we can improve. Without measuring we cannot improve. All over your exams, not only virtual reality exams, other courses also, there is an exam where you are measured your understanding. So only when we give a marks or grade, we come to know how much of your understanding of that particular concept is. Imagine without a measurement, if we can improve, we cannot improve at all, right? So same way here also, we want to improve the experience in virtual reality, therefore we want to measure. That is today's topic. Let me write it down. Let me write it down here. We are experience. We want to measure. All along we have been measuring experiences. Suppose if you have gone to a movie and if your friends are asking how was your experience, you would say the experience is good, bad, or whatever your feeling is. That's also a measure of experience, but that is a qualitative measurement. It is not the quantitative measurement. Qualitative measurement is good. It is it serves certain purposes, but it may not serve our purpose of improving the virtual reality experience. Qualitative measurements will not help in understanding the virtual reality systems. So the measurement, we have qualitative, and quantitative. What we are looking for is the quantitative measurement. Quantitative measurement means we want to give some numbers to the experience. Measuring experience itself is a big challenge. That to quantitatively measuring the experience is even more bigger challenge. The reason is that the experience, it's a mental event. All in our engineering laboratories or science laboratories, we are measuring so many things, but those are physical events. They are not mental events. Physical events very easy to measure. There are instruments available, but it is very, very difficult to measure the mental events because the events are going inside the mind. Okay, not physical event. Let me write it down. Physical event. So how do we measure the mental events quantitatively is the whole challenge now. We want to do this because we want to develop better virtual reality system. That is one of the goals of the entire course. Without measuring quantitatively the experience, we cannot improve the virtual reality systems. That is the reason we want to develop certain methodologies to measure the experience quantitatively, which will help us in improving the VR systems. Let us take an example of looking at a color paper. Color paper. Okay. Suppose if I have a color paper colored red, and I'm seeing it and says this is a red paper, and my friends sees it and say it is a black paper. Suppose if I have a color paper, let us say some color, and I see the color paper and then say it is a red. Let me see. And my friends say it is a black paper. Who is correct? We do not know. Color is a mental concept. Color is not a physical concept. Color doesn't really exist at all. Okay, lights fall on the paper, and then reflection is what we see, and we are taught to name certain reflections as red, black, or green, or whatever it is. So we have learned to give certain names to particular light reflections. That's what the color is. So the color exists only in the minds of the subject. We have our collaborator in the Harvard psychology department. This professor makes a subject see a color photograph and makes them experience and the black and white photograph, even though they are given a color photograph, but what they experience is the black and white photograph, and the vice versa. When they are given a black and white photograph, a collaborator makes a subject see a color photograph. The mental perception can be changed. There are many ways of changing it. For one example is hypnosis. Okay, that is what our collaborator used. So the color is a mental concept. It doesn't really exist. Okay, so to find out whether I am correct or my friend is correct, then we need to talk about, we need to ask the same question to many subjects, and if most of them, majority of them say red, then I am correct, otherwise my friend is correct. So you can see that there is a problem in asking a psychological question, so the qualitative experience. So the color is a qualitative experience. Asking the subjects, it's what the color is, it's a qualitative experience. Right? You can see the problem in naming it. This is a very simple question of asking what the color is. Slightly difficult concepts such as the contrast between the colors gets us into much more trouble. So this problem of measuring the experience quantitatively is thought about by one of the scientists back in 1860s called Fechner. Fechner in 1860s. He thought about this problem and came up with a very powerful suggestion. He looked into this problem and then he observed that the experience proceeds with a physical event. In this case, there is a stimulus, physical stimulus. In our example, there is the light falling onto the color paper. That is a physical stimulus, and then the reflections of the light reaches back to our eyes. Then only we experience. So Fechner observed that if we can somehow relate this physical stimulus to the experience, then we may be able to quantitatively measure the experience. That was his finding. So instead of asking the subjects whether the color paper is a red or black, what he did it's a very intelligent and design. He asked the subjects only yes or no questions. The response is restricted to only yes or no. He designed questions in such a way that the subjects can tell only yes or no answers. Okay. No detailed description is allowed. No detailed description is allowed in his method. So by doing this, he has proposed a method to quantitatively measure the experience. How is that? For example, if you show many colors and one of the color is, let's say, red, then if you ask the subjects whether the red is present or not, the subjects are forced to say yes or no. So that is one task. It is called the prediction task. One color among many colors or they can match the colors. It's called matching task. Match the color to the reference color. There will be a reference color and you need to match the reference color. And the third one could be judging whether two colors are same. Colors are same. So in these tasks, the subjects are allowed to say only yes or no question, response. They are not allowed to make a detailed descriptions. So once yes or no questions, yes or no answers are there, then we can make a statistical inference. It becomes a statistical event, and once we have the statistical event, then we can derive so many mathematical quantities from the statistical event. That is what Fechner's brilliant idea is. So it is almost like the game which we play in our childhood, that at least I remember I have played when I was a child. We asked that our friend to think of a person or a name or an object, and we will ask the question, and the friend is allowed to say only yes or no. The number of questions we ask to find out what the friend is thinking measures our ability to guess quickly, or how effectively we could guess what he thinks about. That is exactly what the Fechner's method is about. The lesser number of questions I asked in order to find out what my friend thinks, the sharper I am, or whatever, right? So that becomes a quantitative measure of my ability or my friend's ability. So we are thinking of similar quantitative method to measure the experience. Okay, I'm making it very simple so that now you can relate to what you already have experienced in your childhood. Once you have this yes or no response, from this Fechner derives a quantitative concept called threshold. Threshold is an important concept in the whole of virtual reality. Okay, so he defines the threshold is certain physical stimulus below which we cannot experience, below which we cannot detect. Below which we cannot experience at all. Right? It's a physical stimulus. and deduction is an experience, the simplified experience where we'll have to say only yes or no. This way, these two things are related, right? For example, if you say, we can put it in a graph. Let's say in the x-axis we have this light intensity, in which we are trying to find out what is the minimum light intensity required for us to detect the light. Let us say in the y-axis we have no and yes response. Let us name the x-axis. Let us say 1, 2, 3, 4, 5. Let us say in one example the subject says no until the light intensity rises from 0 to 2, and then at 2, let us say he detects the light. In this case, the threshold is 2. Let us say this is an arbitrary unit. He is an ideal candidate. If he is an ideal candidate, every time we repeat this experiment at 2 units of light intensity, he will say yes. After 2 units, he will say yes. Okay. So let us assume that he is an ideal candidate, ideal subject. The ideal subject will always respond yes to all the light intensities above 2, and below 2 he will always respond no. But the real subject will not behave the same way. There will be a variation every time you repeat an experiment. Let us say next time when you repeat the experiment, no, yes, y-axis 1, 2, 3, 4, 5, 6, 7. Let us say he responds only at 4 units. Real subject. So his response is changing because there is a noise in the sensory system. Sometimes he responds yes after 2, sometimes he responds and yes as only at 4. There is a variation. Subject to subject, within the subject itself, this variation is there. That is natural. That's a random process, right? So it is essential to measure the same condition many times. Essential to measure the same condition many times. And if we, after measuring many times, if we plot a curve, let us say again x-axis is going to be light intensity and y-axis is going to be the proportion of yes response. Let me say 20% here, 40%, 60%, 80%, and 100%. In the y-axis, I am plotting proportions of yes response at each of the light intensities. When the light intensity was 2 units, let us say there are 20% of the responses were there. When I increase light intensity 4, then there were 60%, and then 6 there were more, and then 7 there were 100%. Okay, let me put it over here. Yes, some other 3, I have some other number. So let us, in a hypothetical situation, let us say this is what the data looks like. Now we can connect these lines and to give you a curve, something like this. So that the challenge is to find out what is the threshold from this curve, because every time the response is changing, the concept that the threshold is changing. How do we find out what is the real threshold? We can assume that whatever that from this curve, this looks like an S curve, so it is called the S curve, S-shaped curve, or it is called the Augy curve, or it is also called the psychometric curve. Okay, one and the same. So from this curve of a particular task, of a particular subject, from this curve we can measure the threshold. Let us say, what is the threshold at 50% of the times the subject say yes. In this case, let us say 3.75 units. And other times this may be more or less. So some subjects consider that at instead of 50, we should consider 75. This is 75%. Threshold at 75%. This is a 50% threshold. So we are going to talk about this problem again in your assignments. You will be given example problems where the concept of threshold will be made very clear. So I am going to ask you to wait until you get a better experience. So at this point of time, the only thing I want to highlight is that threshold is a statistical concept. So we saw that threshold is a measure of mental events, quantitative measure of the mental events, and it is a statistical concept. It is a measure of mental events, let's say experience. Quantitative measure of experience, quantitative measure of experience, and it is a statistical concept. It is not a deterministic concept. That's all I want you to remember at this point of time. Now, threshold, there are two types of the threshold, two types of thresholds. One is the absolute threshold, difference threshold. Absolute threshold is the one below which you cannot experience. Difference threshold is one if you already experience certain light intensity, how much increase in the light intensity is required in order to feel the difference. So difference intensity, difference threshold. Let us define it as minimum difference in the stimulus. Required to experience minimum difference, let me say increase in the stimulus required to experience difference. difference. That is the difference threshold. The difference threshold is called the just noticeable difference. Noticeable difference, or in short, it is J&D. J&D is one of the most important concepts in the whole of virtual reality you may have to learn. This subject of measuring the experience quantitatively is also called the psychophysics. So Fechner is the father of the psychophysics. Fechner is the father of the psychophysics. Father of psychophysics. He has introduced this concept 200 years ago, and in the psychophysics, the one single most important concept is the just noticeable difference. Although the absolute threshold is going to be useful, J&D is much more useful than the just noticeable difference. J&D is much more useful than threshold. So there are a lot of psychophysical data books available for different stimulus, input stimulus, physical stimulus. People have done experiments and then they have measured this just noticeable differences, and then they have put it in the data books. You may have to refer these data books to find out this just notable differences in order to be useful in your design. So let me write it down again. Much more useful than absolute threshold. So mostly we will be using only the J&D. Okay. Now, how do we use the concept of this threshold for measuring the experience? Let us imagine that, let us come up with a scale for experience. I have a ruler scale with me. This scale measures the length. There are marks written over here, 1, 2, 3. It's all either in inches or centimeters it's written. These are the measurements for the length as we have been using it. Similar scale can we come up with for measuring the experience? So the scale starts with 0 over here. Similarly, our scale can start with 0, and that 0 is nothing but the absolute threshold, because below which we cannot experience anything. That's the absolute threshold. From this absolute threshold, what is the minimum increase in the light intensity or physical stimulus intensity needed in order to perceive the next difference? That is the first J&D. Then from the first J&D, again we need certain amount to be increased in order to experience the next difference. That is the second J&D. Similarly, third, fourth, fifth, sixth. These are all first J&D, second J&D, third J&D, fourth J&D, and so on. This is a scale for experience. So, any experience can be measured in terms of number of J&Ds. Let me highlight it. So even though we call Fechner as the father of the psychophysics, before Fechner there was another scientist is whose experimental data were useful for physicists to design this psychophysical field itself. Okay, his name is Weber. In 1800s, he found that J&D with physical intensity, the stimulus intensity, so he actually did one very famous experiment. He used weights instead of light intensity. Weights. See, he took a subject, he put a weight in both the hands of the subjects, let us say W on this side. So he wanted to measure what is the extra weight needed for the subjects to feel the difference. So he's in this case he started with, let us say, 100 gram, and the subjects required 120 grams in order to feel the difference. In the next case, when you put 1000 grams, so this is 110 gram. The next case, when the subject are given 1000 grams, then they needed 100 grams in order to feel the difference. So suppose if we give some symbol like I to the initial weight, and then the final weight with which they can feel the difference is I plus some change in the I, then Weber observed that this J and D, this is a J and D, Di is nothing but the J and D over here. This is a 10 gram, this is 100 gram. Weber observes that J and D increases with a stimulus intensity, but the Di by I, he observed that that is actually constant. In this case, 10 by 100 is equal to 0.1. This case, this is 100 only. 100 by 1000 is equal to 0.1. So Weber's observation is that Di by I is equal to a constant. In fact, this fraction Di by I is called the Weber fraction. Most of the psychophysical data books will mention this Weber fraction. So if we draw x-axis with the I and y-axis with the Di, you will see that it is increasing linearly. This law is called the Weber's law. Weber's law is equal to Di is proportional to I, and the proportionality constant is the Weber's fraction. Weber's law is one of the most fundamental laws, one of the first laws in the psychophysics. Fechner used this law for building the whole field of psychophysics. Although Weber did not come up with the concept of the threshold, but all the data were there for Fechner to invent it and come up with the concept of threshold and just noticeable differences. Apart from this Weber's law, Fechner has come up with another very important observation. He found that in the scale of experience, when we have this J and D, number of J and Ds, 1, 2, 3, 4, 5 J&Ds, the scale of experience. Let us also call that as a sensation magnitude. These are all some of the terminologies you may have to get used to it, so that when you come across in the literature, in the reference books, you know what we are talking about. Right? He observed that the physical stimulus, is not uniform. For example, let us say this is a light intensity. In this case, this is going to be some 10, 20, 30, 40, 50, 60. Then the J&Ds are result of non-uniform increase in the physical stimulus intensity, in fact. So this can be put it in the another graph. Stimulus intensity, let us say I, and let us say this is nothing but the psi, number of J&Ds, basically number of J&Ds above threshold, number of J&D above threshold. Let's say 1, 2, 3, 4, and what he found out that it is not linear, it is saturating over here. As the J&Ds increases, more and more increase in the stimulus intensity is needed, is what Fechner's observation is. In fact, he says that there is a logarithmic relation between the psi and the I. So if you take off log of I and then psi over here, then there is a linear relation. So this observation can be put it in a equation is proportional to log of I. This relation is named after Fechner, and it is called the Fechner's law. Fechner law is that the sensation magnitude, the scale of experiences, the J&Ds, is directly proportional to the log of I. It is not just proportional. So again, Fechner's law holds good for various stimuluses, but there are some few exceptions. For example, pain is an exception. Exception to the Fechner's equation. And also, Fechner's assumed equal interval between the J&Ds, which is not correct. Equal interval between the J&Ds is not correct. So if you look at this interval, he assumed this to be equal. That's what Weber also has found out, and he assumed Weber is correct. Therefore, he derived this relation of logarithmic relation between the intensity to the sensation magnitude, and is not necessarily correct, is what the later researchers have found. In fact, there's another researcher called Steven. We are going to talk about, he refined the Fechner's law and came up with his own law called the Stevenson Law. He says that the sensation magnitude is directly proportional to the, not logarithmic of I, but to the power of I. There is a power relation exists between the sensation magnitude and the intensity, is what the Stevenson had come up with. Stevenson is about very recent time, maybe about 50 years ago. He was a professor in the Harvard. He has generalized Fisher's law, and in fact, there are no exceptions found for Stevenson laws. All the physical stimuli follows this power law of psychophysics. For each of the stimulus, people have measured this n, and then they have just listed out. For example, loudness. N is considered as 0.6, brightness N is equal to 0.5, and heaviness N is equal to 1.5. Length measurement N is equal to 1. While deriving this number, Stevenson has slightly modified Fechner's equation, Fechner's experiment itself. He did not find out the J and D. Instead, he considered magnitude estimation task. It's slightly different estimation task. So in the magnitude estimation task, people are given an object and they are given a reference object. This is a reference. They are given a number. With respect to the reference, they are asked to a quantitative measure of another object. Let us say the subject gives 120 or somebody else will give 140. Okay, so this way there are some biases inherent in the Fechner's experiment are avoided. Okay, so in fact in Stevenson law, the y-axis is mentioned as a magnitude estimation. This also is the same as the psi. It is not just the J and D. Then here it is considered as I. Then there is of course a linear relation for certain things. For example, the length measurement, what we talked about it as a linear measurement. For some other things it increases. For some other thing it is actually decreases. So here n is greater than 1, n is greater than 1. Here n is less than 1, n is less than 1. If n is less than 1, then more intensity is required for increasing the experience. For conditions where n is more than 1, less and less intensity is required to experience and more the physical stimuli. So in most of the conditions, Stevens data is preferable wherever is available. Stevens data is preferable to Fechner or Weber's data. That is because of the way this magnitude estimation task is done. This is slightly better than the J&D task. So we will stop here. We initially started with looking at how to measure the experience quantitatively. We came up with this concept of threshold, and then the derived concept of J&D, which is a much better concept than threshold itself. We looked at the Weber's law, we looked at the Fechner's law, we looked at the Stevenson law, and then we looked at what are the problems with Weber's law and Fechner's law, and how Stevens refined these two laws to a much more general psychological law. If you look at the literature, the data for all the three laws may be available. So you should know which data to use in which situation. In fact, all the three laws are called classical psychophysics. The concept of threshold itself doesn't exist is what the reason psychophysiologists say. That belongs to the advanced psychophysics course, which we offer as a separate semester course here in IIT Madras, which you don't have to worry about. If you are aware of this basic fundamental three laws of psychophysics, classical psychophysics, that is good enough. That will help you to design better virtual reality systems.